Hello, hello, and welcome to Thursday's live stream. We are covering today, it's going to be short and sweet. We're going to be talking about potometers and how they work, how they're set up, and we're going to be talking about how you can improve accuracy and, more importantly, how you can improve your marks when writing about accuracy. So this is what we're doing. As normal, if you've got capital, use capital for immediate questions. Feel free to give me topic requests. I have a look at them afterwards and I post in the community chat which ones have already been covered by videos. And from those topic requests, I then produce the list of 3 that you then get to vote on. I get the impression it's quite a close run thing on the community poll for Tuesday's session. So do go and vote on that. Give me a thumbs up if I've just clarified something for you. It's just really lovely for me. I'm just going to say that and leave the other questions to the end. I'm also going to say, if you're not subscribed to my channel, can you subscribe? And the reason is because I frankly have nearly zero interest in social media. But the reason is that I absolutely believe in biology being accessible to everybody. And I really want my message to get out there. I am not doing this for the money. I think since I've monetized, I've earned about £80 in about 10 months. I ain't doing this for the money. I really want the message to go out there. So if you can encourage friends to subscribe and share my stuff with them, gossip away about Biology Carol, I would love that. And I'm hoping they will get something out of it too. That is my ultimate aim, that you get something out of this. So with no further ado, let's get on with this. I've already said what we're going to do. We're going to do a little bit of potometer maths as well. And hopefully this whole aim is to get increasing marks in the exam. So potometers, I hope this bit doesn't come as a surprise to you. They measure transpiration. And transpiration is the evaporation of water from the leaf via the stomata. But the bit in the brackets, I just want to point out to you that all of these cells, the palisade and the spongy mesophyll cells, the water evaporates from the cell walls of these cells, where they are the boundary of the cell wall and an airspace inside the leaf. So wherever any of these cells surround an airspace, that is where the water will be evaporating from, into that airspace, and then it leaves the leaf via the stomata, down a water potential gradient. So how do potometers work? Really, basically, it is because there is a tight air seal between a tube of water and a leafy shoot. That's all a potometer is. And added on to that, there has to be some means of measuring either the water loss. Let's just say there has to be some means of measuring the water loss from the leafy shoot. Now that is either by mass, and I'm going to show you some examples of potometers in a minute. And so the units of mass would be either milligrams or grams. We got a question?
Yeah, just quickly, is this for year 12 or year 13?
This is year 12. Year 13, obviously you need to know it. Year 13, you might want to rejoin in about 10 minutes time. I'll probably be talking about accuracy by then. Just a thought. Or by volume of water. And those units might be micrometers cubed or millimeters cubed. So some alternatives for potometers. This is about as basic as you get. You've got your tube of water, you've got your leafy shoot, you've got a calibrated something or other that allows you to measure the volume of water that is taken up. This is another simple one. Tube of water, leafy shoot, airtight seal because of the oil. And here it's simply that mass is lost, and you're assuming that the mass lost is the water lost from the leaf. Here's a slightly more complicated one where you've got a tube of water, leafy shoot, as well as the calibrated pipette thing here where you can measure the volume, you've also got this reservoir. And this addition allows you to top up the water in the whole system and therefore bring the water level in this pipette thing, the measuring device, back to close to zero so that you can repeat the experiment. And finally, here is the version that you're most likely to see in an exam paper. Notice tube of water, leafy shoot, and a way of measuring. Here you're measuring how far an air bubble moves. And here you've got, instead of this filter funnel shoved into some rubber tubing, you've got a posh glass reservoir, which does exactly the same job, because when this tap is opened, water is allowed into the system, which then moves the air bubble back to the beginning of the ruler so that you can repeat your experiment. These two very, very simple versions here, it's a lot more difficult to be able to repeat your experiment time and time again. That's what the reservoir is for. So, in terms of this kit that we use for measuring transpiration, and in terms of the validity of this method, does it make sense that our assumption is that all of the water taken up by the plant and lost by the plant is because of transpiration? Remember that validity is being sure that you're measuring what you think you're measuring. So, for it to be valid, you're assuming that the only reason water is lost is because of evaporation. And therefore, does it make sense that you are assuming that all the plant cells must be turgid? They've got to be full of water. This plant shoot should be a well-watered plant shoot. Otherwise, this air bubble will move because the cells are filling up with water and not just because water is being lost by transpiration. You're also assuming that no water is being used in photosynthesis or being produced in respiration. Now, this is a bit of an ask, but it's worth you knowing, just so that you don't dismiss any experiment on transpiration using a potometer. Over 95% of the water that is taken up by the shoot, let's assume that every cell is turgid, over 95% of the water travels through the leaf and goes out via transpiration. And the other thing that you are assuming is that there are no leaks. There isn't any other reason that this air bubble is moving. So how to set one up? I found a nice simple video, which I've put the link to in the description, because this experiment is the one that you are least likely to do, or one of the ones you're least likely to do in a lab, because they are frankly a nightmare for teachers and technicians to set up. But you are required to know how they work. Colorimeter, you've almost certainly all used. So here we are, just reminding you of this kind of setup. So here is the method, and most of these you need to know why they are done. So I'm going to go through them. The whole kit needs to be assembled underwater. It requires one big bath of water for the technicians or teachers or you to set them up. And that is so, sorry, I should have said, and that is so that there are no air bubbles anywhere in the system. Secondly, you have to cut the chute underwater so that there are no air bubbles taken up into the xylem, because otherwise an air bubble in the plant could stop the passage of water up through the leaf, or at least partially stop the passage of water through the leaf, and therefore slow down the rate of transpiration. Next, you have to cut the chute on a slant, and that's so that there is a maximum surface area for absorption of the water into the xylem. You've got to ensure all the joints are watertight and airtight. You need to dry the leaves. You want to be sure, especially if you've got this sitting on a balance, that the only reason that water is being lost from the balance is because of water being evaporated from the leaves because of transpiration, and not because you're losing all the water that is sitting on the surface of the leaves. That's evaporating also. You need to close the tap to the reservoir, otherwise if this reservoir tap is open at the beginning of the experiment, your air bubble is going to go flying out of the capillary tube and you'll lose it and have to kind of go through that part of setting up the kit again. You need to record the start position of the air bubble, or in some of the simpler potometers, the level of the water. And importantly, because you are going to be calculating the rate of transpiration, you need to record the time taken for the bubble to move a certain distance, or in the simpler potometers, for the water level to drop to a certain level, or for a certain mass to be lost if you've got your little potometer on your balance. And finally, if you are investigating the effect of certain variables on transpiration, which is highly likely, so variables such as temperature, wind speed, humidity, probably not in a school lab, or light intensity, you can only change one of those variables, which is, of course, the independent variable, the one I have decided to change. Independence starts with I. And all the others have to stay the same. They have to be controlled variables, because that is another key way, if you remember from my last live stream, as to how you keep your experiment and therefore your data valid. It's only the rate of transpiration is only changing because one of those variables is changing.
Do they need to know this method?
You need to know, right, I'm going to tick, because practically, right, here are the popular ones that are really useful for you to know. That the chute has to be cut underwater so that no air bubbles go into the stem, that the chute is cut on a slant to increase the surface area. This is another really good one to have. Those three are probably enough for you to get by on most exam questions, knowing why they're all important. But the other ones, these ones particularly, are other ones that you could include. These ones over here, 7 to 9, are really about how you use this kit to measure the rate of transpiration. I hope that, and do it in a valid way, because you're only changing one variable. Hope that's a bit clearer. Okay, oh, and finally, 7 to 10. And you clearly have to repeat your experiment just to make sure that you don't, so you can identify anomalies and calculate a mean, for example. So, little bit of maths, particularly with the kit that you're likely to come across. So that picture that we had in the previous slide. Remember that rates are the change in something, anything it could be. In this case, it's the change in the distance that the air bubble moves, or the change in the mass, divided by time. I sometimes find changing the word rate into speed helpful, because the most common units of speed are miles per hour. And miles per hour are literally written miles. This division line is the per, and it's miles per hour. And it always reminds me that I have to have a time for rate, and I have to have a change. So obviously miles per hour, the number of miles that you cover in however long it takes you. So just a little thought as a way of remembering how important the time aspect is for change, for rate. So in terms of mass, it would be mass per unit time. So for example, grams per hour or milligrams per minute. And I just want to point out that this minus sign here means divide time. Time is on the bottom of this fraction. You are dividing miles by time. So divide by time. That's what that minus sign means. Or else, and that is for this particular kind of setup, obviously, where you're recording the mass change. Or else we're talking about volume change per unit time. So, for example, millimeters cubed per minute. And that is for your, the more standard kit. So if you were calculating the rate here, you would simply be recording what mass is lost and over what period of time. And therefore, you would simply divide the mass lost divided by the time to give you that rate. When it comes to this kind of setup, it gets a little bit more complicated, but not too much, hopefully, because you have got to be able to calculate what volume of water is lost, as well as knowing the time. So let's say a bubble moves 8.5 millimeters in 12 minutes along this ruler. Notice that 8.5 millimeters is not millimeters cubed, it's a different unit. It's a unit of distance, not of volume. And therefore, we have to be able to calculate the volume, not the distance. And here it is really worth remembering that this capillary tube is actually just a very skinny cylinder. And you probably know how to calculate the volume of a cylinder, assuming that you are given the diameter of that cylinder. Can I just point out, for those of you that are you're one step ahead of me and kind of going, oh my goodness, we've got to calculate the rate, we've got to work out the radius. Obviously, that's not hard. But why don't they give us the radius rather than the diameter? Well, if you think about any tube lumen, you don't know where the flipping center of that lumen is. It's actually impossible, nearly impossible, to accurately measure the radius of any lumen, the hole down the tube. The only thing that can be measured really accurately is the diameter. And that is why this measurement is put in exam papers, not just to trick you. All right. But you do, obviously, if you're one ahead of me and realizing, oh, we've got to calculate the area of a circle and then times it by the length, because, of course, that is what the volume is. So the area of the circle is pi r squared times length. And therefore, you'd have to know that pi is 3.14. Could do 3.142. I wouldn't go any further than that. Pardon? 3.142.
Yes.
3.142 times by the radius squared. There's your area of the circle, times by the length. You've now got your volume. And this is what was in my calculator when I did it. Notice I am not rounding up or down until the end of the calculation, because I've now got the volume. So now I need to divide it by the time. So divide it by 12, and that gives you this number. And we now have the units of millimeters cubed per minute. And I've rounded that to 2 decimal places, which seems reasonable. Okay, so now let's move on. Told you this was going to be short and sweet, to improving accuracy. Accuracy is how close you are to the true value of whatever it is you are trying to determine. And in your exam paper, the accuracy, they might ask you to how you could improve the accuracy of the data collection, Or they could ask you, oh, so for example, you know, measuring lengths of beetles, for example, or measuring O2 volumes produced in a photosynthesis experiment, or measuring the mass of water lost in a transpiration experiment. Just some examples of things that would be raw data that you're collecting. The outcome of you, or they might ask you to improve the accuracy of the outcome of your investigation. And the examples for this are things like, oh, what is the optimum pH in an experiment where there is the rate of activity of an enzyme is measured at certain pH intervals? Or, for example, the determination of an unknown solution concentration using a calibration curve. Two particular question types, and I'm going to cover both of them. So for this question type, you are trying to work out how to make your raw data. So for example, you're trying to discover what the average length is of an adult beetle. Well, you're going to want to increase your number of repeats. We're going to talk about reliability probably, or maybe next week or the week after, but this is an aspect of accuracy. If you're wanting to know the oxygen production by photosynthesis at a particular light intensity, you're not only going to do that experiment once, you're going to repeat it. Because the more repeats you do, it means you can identify anomalies and calculate a mean. And that mean will be more accurate the more repeats you do. Another way of increasing the accuracy, particularly for something like beetle length or anything with a living organism, is actually, are you able to identify them accurately? Have you got some kind of identification system that you can use that means that you are sure that you're measuring the right flipping beetles? And another thing is you should increase, or you could increase, the resolution of your measuring equipment. So again, if you were measuring the length of a beetle, one, decide exactly what measurement you're going to measure on the beetle. And then also possibly, rather than doing it with a ruler, you could do it with, for example, a pair of calipers, which will just be that much more precise because their resolution would be higher. Remember that the resolution is the smallest division that your piece of equipment will measure to. So, for example, a standard ruler, 30 centimeter ruler, the resolution of those rulers is 1 millimeter. It's the smallest division on the ruler. The resolution of most lab balances are either 0.1 or 0.01 of a gram, depending on how many decimal points the display goes to. On this side, improving the accuracy of something like an optimum pH, you might have a graph something like this. And I'm going to say to you, look at the points. Oh my goodness, don't look at this line. This line is not a line of best fit. It is a frankly horrifying line because AQA would actually allow you either to draw a nice smooth line of best fit, or they would allow you to join the dots using a ruler. But joining the dots freehand like this is a guarantee only of not getting a mark. I'm going to be honest with you. A line of best fit should show clearly the trend of the line, but should not religiously go through every point, but it should have probably an equal number of points on either side of the line. It is about the most arty-farty thing that you have to do in science. So to be quite frank, as long as you don't do this and you do a vaguely decent job of drawing the trend, you'll get the mark. Also, you never, ever extrapolate beyond the points that you have, your experiment has covered. So, but sorry, back to optimum pH. Well, this graph, the points on this graph immediately tell me that the optimum pH is going to be between 6 and 7. And it's not between 7 and 8 because the rate at pH 6 is much closer to the highest point than is the rate at 8. That tells me that the peak is going to be this side of pH 7. It's going to be between 6 and 7. But how could we improve the accuracy of that? Well, that is done by carrying out further experiments of the enzyme's activity at pHs between pH 6 and pH 7. pH 6.2, 6.4, 6.6, 6.8, for example. And then your line of best fit will be far more accurate. You'll have a much more accurate determination of the optimum pH.
So this stuff, is it really similar for OCRA? It's the content
yes,
really similar.
Yeah, absolutely. In fact, almost OCRA, I think, have probably some of the trickier questions on this kind of thing. They are certainly covered in AQA, but OCRA, I have noticed, ask about data collection and they ask about things about the outcome of your experiment. And it's well worth you reading the question and realizing which one they are asking about, because then you'll be sure of giving the right answer. So determination of a solution concentration using a concentration curve, let's say, and I know this is rather small, let's say this is my concentration curve and my unknown solution had an absorbance of something about 1.6. And so that gave me a concentration of, I'm guessing, around 70. To make that concentration estimation more accurate, you can see that the concentrations of the known solution that were used to make this calibration curve, there was one down here below 50 and there was one up here at about, I don't know, about 80. Well, then you would want to be doing measuring the absorbance of more known concentrations between those two concentrations that are on the calibration curve. So I'm hoping, there we go. So test more pHs or solutions of known concentration between kind of like the values on either side. But if you're looking at optimum, you need to know which two are the right two to do more measurements between. Hope that makes sense. And that is about me done for improving accuracy. I think we're about there. So I think we are at any questions. So I'll just give you a minute or two, but I'm really hoping that that will have clarified, it will have demystified potometers, and also it will have hopefully clarified what accuracy is and what you should be addressing if they're looking for you to improve the accuracy of data or to improve the accuracy of the outcome, the aim of your whole experiment. How are we doing? Everything nice and quiet?
Yeah, well, it'll take them a minute to
okay.
questions. You've got some thank yous.
Have I got some thank you for the thank yous? Do you know, I do really appreciate it. You've got no idea how much that means to teachers. Every now and again, I'd get a thank you as students walked out of my classroom, and I would always say thank you for the thank you, because it was always much appreciated. How are we doing? Any more topic requests? Okay, hopefully I have clarified things. Right, I'm going to love you and leave you, let you get on with your evening. Have a look at the community tab for the poll. It's looking very close. Please subscribe, get the message of Biology Carol out there. I really want people to be able to do biology. See you on Tuesday.